Hello and welcome to part 1 of Dev Maths and Stats Refresher Course Lecture 3. In yesterday's lecture, Lecture 2, we considered the special case where we have functions of just one variable. But in the real world, the things that we're interested in, such as poverty or growth or nutrition or education, all these things generally depend on many different factors. And what makes social science so useful but so difficult is that it can deal with many different factors. So when we come to maths and calculus, differentiation involving many factors and many variables is referred to as partial differentiation, and we're finding partial derivatives. So that's the main focus of this lecture. So in the first section here, we're going to have a conceptual section as usual, and this is talking about how you visualize partial derivatives. Then we get on to the nitty-gritty maths of how you find partial derivatives, applying the similar rules that we had yesterday to the situation of many variables. Then we look at some applications of putting that to work in different topics. And then in the last section, we look forward slightly to the work in the forthcoming lectures on optimization by seeing how we can use differentiation to describe different features of functions. So let's get started in the first section with visualizing partial derivatives. If you have got Maple and you want to follow this, you can just click on the red areas and press return. In the PDF version, all this is already expanded, so you can just view it, but you won't be able to see the graphs dynamically. So what we're doing here is we're setting up some parameters. So A and B are 1, delta 0.5. Here's a function we're going to look at. So here's what I mean by a function of two variables. Function f is a function of x and y. You can see it's a kind of quadratic variable. The domain, remember that word means what range of values do you have that x and y can range over. So we're looking between 0 and 2 in each case. Then we're going to find the partial derivatives, which we'll go into in the main part of the lecture. This is going to be the tangent plane. I'll explain that in a moment. And here's the actual surface. Sooner or later we'll actually see the graph appear with any luck. This just sets it up and makes the colours hopefully visible. So here I think we should get the graph. So let me try and explain what we're seeing here. So we've got the graph of this function defined up here in blue, but now the function has got two inputs or two arguments, x and y, and the height up here is the value of the function. So if we choose any combination of x and y, then the function will tell us how high we have to come. So we can see at the point when x is y and 0 is, and when x is 0 and y is 0, we have the function is 0. As x and y get greater, the function gets greater as well. So rather than a curve, we have this curved surface, which is the graph of the function itself. Then if you remember, when we talked about gradients of a curve yesterday, we had to put a tangent against the curve. But here we have got, instead of a curve, we have a curved surface. The equivalent of the tangent line is a tangent plane. So it's like a flat surface. Imagine a book or a mobile phone or a tablet computer. You're pressing it against this flat surface at the point you are interested in. So it just touches. And to make it more concrete, I've chosen one particular point, one combination of x and y, which I can see here. It looks like the point 1, 1, in fact, I've chosen. And that was where, yes, that's because we had set a and b is equal to 1. So this is the initial points here. And delta was just saying how much then we're going to increase from that point. So we take the point 1, 1 here. This height of this yellow line is you substitute 1 into the 1 and 1 into the function. You find the height of this line. Looks like approximately 2, perhaps that's right. And then you put this brown flat surface against the curve here. That's the tangent plane. And then what happens is you consider moving away from that initial point of 1, 1. But what makes life interesting when you have more than one variable is that there are many different directions you can move in. So we consider some special directions. First we say, let us keep y fixed at 1, and we move only in the x direction. If we do that, we increase x by 0.5 this way. It means we move to this position, and now this is where we are. We can see that the function has increased, but as we move along this slope, we can see that if you imagine the slope of this flat surface, in this direction it's sloping upwards just gently like this. So we follow that flat surface along, we gradually move away from the curve. You can see a gap here, and the value of the function moves up slightly, or the value of z moves up slightly along here. So that's the slope if we go in the x direction. Alternatively, we can keep x fixed. So keep x fixed at 1 and move in the y direction. And what we find here is that it's sloping up more steeply in the y direction. So the slope of the y direction is steeper than the slope in the x direction. Now, what we have here is, when we differentiate this, we actually have two derivatives. There's a derivative in the x direction, a partial derivative in the x direction, saying let us keep y fixed and increase x. And that's positive because we go upwards, but it's quite small, so gentle upward slope. The partial derivative in the y direction is positive again, but much steeper. Okay. Hopefully that's clear, but please feel free to play around with this, see if you can visualize this yourself, if you can move it around, or you can ask me questions in the live section tomorrow. Before I move on from this to the actual nitty-gritty, I want to show you a shape that's really hard to draw on that whiteboard, but causes problems in optimization particularly. So I'm redefining the function here. So again, it's a function of x and y, it's a quadratic. I'm going to redefine the range we're looking at. So I'm starting at the point 9 and 24, and I'm going to increase by 8 when I work out the two derivatives. And then go back and find the partial derivatives. So we go back to here and execute these commands, but now we have a new function. So partial derivatives are new, this is all new, this is all new. Eventually it's going to draw it now. Look what we have here. Now this is a much more complex shape. And this kind of shape is sometimes known as a saddle shape. If you've ever ridden a horse or seen people riding horses or other animals, it's the shape of a saddle. And the problem is that in some directions it curves U-shaped like this, in other directions it curves in the other sense, like an upside down or inverted U. So I've chosen this point now, which is, I can't remember what it was, it's like 8 and 20 something. What was it? 9 and 24. So we have the point x is 9 and y is 24. That's the point here. And then we have to find the value of the function, making sure that we have this thing the right way up. That's negative. It's positive there. So at this point, you can see that z is this way up. So at the point 9, 24, the value of the function is negative. So I hope you can see that. The value of the function itself is negative there, because the purple shape is the function. But what's happening to the slope? Well, what makes this difficult is you have to imagine that onto this complicated curve here, we are placing a flat surface, the tangent plane, so it just touches at this point. So because it's curved in a strange direction, it's going to cut through. But at this point, it's just touching. And then, starting from the point 9 and 24, we move in the x direction and we move in the y direction along this tangent plane. We see what happens. So you should be able to see from the way this is fitted onto the plane that if we keep y fixed and we move in the x direction this way, then we would move up. So you're moving in this direction, the x direction, it goes upwards the way that plane is tilted. So again, the partial derivative in the x direction, we say the partial derivative with respect to x, keeping y fixed, is positive, but quite small, it's a gentle slope. Then we imagine keeping x fixed at 9 and increasing y this time. Now we get a completely different picture, because if you go in the y direction, you're going down, and down quite steeply. So the partial derivative in the y direction would be quite large and negative. So you've got a positive derivative in the x direction because it goes upwards, and a negative direction, a derivative in the y direction because it goes downwards. Okay. So hopefully that gives you some sense, some intuition of what's going on when you find the derivatives in these different directions, because if you can develop this intuition, it gives you a good feel for what we're trying to achieve when we do the optimization later on. Okay, so in the next section we'll move on to the more nitty-gritty of how you actually apply the rules and find derivatives. But for now, thanks for watching.